Hello everyone and welcome to my FoodSim 2020 presentation. My name is Viviane and I'm part of the BioTeC Plus team. Today I present to you our work on introducing sexual selection into genetic multi-objective optimization algorithms in order to upgrade the mating step. The outline of this presentation consists of an introduction where I'll present to you the basic concepts of multi-objective optimization, genetic algorithms, and the concepts of natural and sexual selection. Subsequently, I present to you how and why we would want to combine natural and sexual selection into genetic algorithms, and I accordingly present our newly developed genderless sexual selection approach. Eventually, we'll apply the presented algorithm and concept on a scalar case study, of which the results will be discussed. And to conclude, I'll give a quick summarization of the work that is done, but also an outlook on further research. Now, in today's day and age, it is of the utmost importance that processes are operated as optimal as possible. But what actually is optimal? You can imagine that you can optimize a process regarding a multitude of objectives. For instance, its impact on the environment, or its added value to the society that's impacting, or of course, how much profit you can expect from the process. Now, it shouldn't have to come as a surprise that these types of objectives often have different and conflicting optima. So we end up with a multi-objective optimization problem where there's no longer one unique optimal solution, but rather a set of equally optimal solutions called a Pareto front. Generating a sufficiently accurate approximation of the Pareto front is the ultimate goal when solving a multi-objective optimization problem. Now, for the generation of these Pareto fronts, genetic algorithms are often used as the go-to optimization algorithm. Their main functionalities are based on Darwinian evolution. The initialization step consists of the generation of a random initial solution population into the feasible space. Subsequently, the solutions are used to create new offspring solutions. This can either be done via a crossover or a mutation step. In order to converge to the Pareto front, eventually we need to select only the n best or fittest solutions of the population. Now, a fit solution is one that is on one hand well converged to the Pareto front, but on the other hand also contributes to the overall solution diversity, because you want to approximate the entire length of the Pareto front and not only a small section. The convergence of a solution is quantified using non-dominated sorting, whilst the diversity of solutions is quantified using the Krausen distance. Now, knowing these two parameters, the algorithm is then capable of selecting only the n fittest solutions of the population, and by repeating this process, eventually the solutions will converge to the Pareto front and retain a high solution diversity. Now, like I said before, genetic algorithms take their inspiration from Darwinian evolution, more specifically natural selection. During the optimization process, only the fitness of the solution itself is taken into account, and based on that, it is allowed to survive into the next generation, or it is killed off, as it were, by not being selected. Darwin, however, acknowledged the second force happening in nature, which he attributed to have even a more profound influence on the evolution of species than natural selection, and that is sexual selection. Now, the peacock is one of the better examples to show how far sexual selection can drive things, and in fact how a natural species can become due to it. Now, as you know, the male peacock has massive tail feathers. Now, if you look at this from a pure natural selection point of view, you can imagine that these tail feathers can actually become quite cumbersome in a precarious situation. So the fox, he's loving it. So you might expect that the species would evolve to display a less pronounced tail feathers. The peahens, however, the female peahens, who look, by the way, a lot less interesting than their male counterparts, but they just pure love it. Those big tail feathers, they will always prefer the male with the larger and longer tail. And as a result of this, these types of males are more likely to find a partner, reproduce, and so their genes, also those of the long tail feathers, are more clearly present in the entire population. Now, just to recap very quickly, in nature there are two forces at play, natural selection and sexual selection. Natural selection regards the individual's own capability to survive. Now, in nature, this translates in being able to survive long enough to reproduce and pass along their genetic information. Whereas in the case of the genetic algorithms, this is obtained by being selected as a partner, as a parent solution for the next generation. Sexual selection, on the other hand, looks at an individual's chances of getting a mate or a partner. Things like look, character traits, or how well you are at courtship come into play in this case. In the case of genetic algorithms, however, this selection step is not really present, as once solutions have been selected as parents for the next iteration, solutions are all equally likely to reproduce as they are combined randomly. Moreover, we see that evolving species change their partner preferences over time. Species that are fairly new and that are still establishing their own traits often regard different or complementary partners as the more attractive ones. They go into explore mode, and during the optimization of a problem, in the early stages of the optimization process, we also want solutions to diversify and explore the feasible space so that we can discover the full length of the Pareto front. More established species, on the other hand, prefer similar partners so that the population stays consistent. They want to exploit them. If we look at the algorithm at the optimization problem again, once the solutions have diversified sufficiently, we want them to converge to the Pareto front as much as possible. The previous attempts to include sexual selection into genetic algorithms employed the gendered population, but we felt that this subdivision of the solution population into female and male solutions was detrimental for the inherent randomness of the algorithm. Therefore, we introduced a genderless sexual selection procedure that precedes the crossover step. Now, once two solutions are selected for the crossover step, they are randomly assigned a gender, which they only keep for the duration of the courting and crossover procedure. Once they go back into the main population, they become genderless again. Now, as a nature, we then assess if the female solution is likely to pick the male solution as their partner. Corresponding with the two scenarios that we've presented before, being the exploration and the exploitation phase, we also distinguish two different courting scenarios. Now, our basic assumption is that females are looking for a partner that is more attractive than themselves. Attractiveness is quantified using a popularity index, which is basically the sum of a solution's non-dominated rank and its crowding distance. The higher the popularity index of a solution is, the more converged and diverse it is, and so does the more attractive it is. Now, the first courting scenario, of course, occurs when the male solution is more attractive than the female solution and thus has a higher popularity index. In that case, the female solution is very likely to select this male solution as a mate. By generating a random number between 0 and 1 and comparing it with the likeliness of selection, the final decision is made. Now, as the non-dominated rank of a solution has the highest influence on the value of its popularity index, we see the most diverse collection of popularity indexes if solutions are scattered over a multitude of non-dominated fronts. And this is more likely to happen during the first stages of the optimization process. In this stage, we indeed would prefer solutions mating with solutions that are highly different from themselves and thus going into exploration phase. The second courting scenario occurs when the popularity of the male solution is lower than that of the female solution. And in this scenario, the female solution is less likely to select this male solution as its partner. The only thing that could persuade her is if the male solution has a significant difference in traits or optimization variables. Therefore, attractiveness is now translated in a big difference of optimization variables. And the magnitude of this difference influences the likelihood of a female solution selecting the male one. Now, once solutions start converging to the Pareto front, the difference in popularity indexes will decrease as the number of non-dominated rank will also decrease. And so this courting scenario will most likely take place during the second stage, the exploitation stage of the optimization process. Now, the proposed method is applied to the scalar construct study. It consists of two objectives that need to be minimized, and it also considers two inequality constraints. Both the genderless sexual selection algorithm and also a benchmark NSG2 algorithm are applied to this case study, but in order to compare their performances, three performance parameters are followed throughout the optimization process. The first one is a fraction of Pareto optimal solutions, which gives us an idea of conversion speed. Then we have the mean ideal distance, which gives an idea of convergence, and the spread of non-dominated solutions is used to quantify diversity. Now, if we look at the results, we can see that both algorithms are capable of approximating the Pareto front. The genderless sexual selection algorithm slightly outperforms NSG2 here on this plateau. Now, if we look at the evolution of the performance parameters, we can see more profound differences. We repeated the optimization procedure 10 times, and we can see that whereas the NSG2 algorithm required 30 iterations on average to obtain a solution that was fully non-dominated, The genderless sexual selection algorithm only required 20. Now, especially if you're looking at computational expensive optimization problems and simulations, this influence of this faster convergence speed will become very significant. Regarding the overall convergence of solutions to the Pareto front, we can distinguish two consecutive events taking place. The initial decrease in mean ideal distance is mostly due to the solutions converging to the Pareto front, whereas a subsequent increase is more likely due to the diversification of solutions. And again, we see that the genderless sexual selection algorithm displays on average a slightly higher Pareto front exploration than the original NSG2 algorithm. Now, to conclude, genetic algorithms are widely used optimization algorithms in the context of multi-objective optimization. They are mainly based on the selection of the fittest or natural selection. However, in nature, also sexual selection takes place between individuals of a species. Therefore, we introduced a genderless sexual selection approach in order to make solutions make a well thought through partner choice. The attractiveness of a solution is quantified using a popularity index, and we've distinguished two different courting scenarios. The first one emphasizing the exploration of the feasible space, while the second one emphasizes the exploitation or convergence to the Pareto front. As a result of this, we can see an increase in convergence speed as well as an increase in Pareto front exploration. Now, if you look just a little bit further down the line, it has to be noted that unlike in nature, our definition of attractiveness is still highly based on the survival traits of the individual itself. This could result in overemphasizing fitness too much. It would be desirable to modify the popularity index to include a solution's potential. Now, if we look, for instance, at this male and female solution, the female solution dominates the male solution, so its popularity index will likely be higher. So the female solution is less likely to select a male as a partner. However, if you look at the male solution's potential to diversify the overall population set, it's a lot higher. Now, we would want to see that this male solution, although it has a lower popularity index, is still considered to be attractive because it has a lot of potential, but this is now not the case. Now, to end with, I would like to thank the FlexiBee project, the BioTeC Plus team, and FWO for supporting this research and making it possible. You can always contact me and my colleagues on these email addresses, and you can find us online on Twitter at KU Leuven BioTeC and also on cit.kuleuven.be/biotech. Thank you very much. If you have questions, please get in touch.